Welcome to From QA Challenges to Innovation with PRIZ, where quality challenges spark innovation. Today, we'll explore how seemingly minor issues, like movement in manufacturing processes, can lead to significant quality problems. We'll delve into a fascinating scenario involving silicon wafers, where a hidden movement issue during the loading of wafers into a furnace led to false temperature readings and overheating. Using the PRIZ methodology, this persistent quality problem was unraveled, highlighting the power of systematic analysis tools in uncovering hidden dynamics within complex systems. We'll examine the contrasting perspectives of structured analysis versus intuitive problem-solving to show how they can collectively transform persistent QA roadblocks into scalable solutions. In just a moment, our two co-hosts will join us to deliver well-balanced, respectful insights, weaving together structured thinking and forward-looking strategies. Dr. Thinkman and Debra will be dissecting this intriguing case, sharing how the disconnecting of a thermocouple during specific times provided an innovative solution to a perplexing issue. Let's start by handing over to Debra and Dr. Thinkman as they embark on this insightful dialogue. Here we go. I'm Dr. Thinkman, and joining me today is my colleague Debra. Today we're exploring how movement itself can become the hidden villain in manufacturing processes, and how systematic problem-solving tools can reveal solutions that have been hiding in plain sight for years. To demonstrate this concept, Debra and I are going to play out a real-world scenario that perfectly captures this principle. I'll be taking the role of Steve, a frustrated engineer dealing with a persistent quality problem, while Debra will play Sean, who discovers the breakthrough using PRIZ methodology. Let's see how this unfolds in what we might call the mystery of the moving wafers.
Picture this. It's lunchtime rush hour in the cafeteria. You're juggling your tray like a magician, keeping an eye on your soup, answering a phone call, nodding to a coworker, and narrowly avoiding a puddle of ketchup.
Great. I'm staring at the soup splatter on my shirt. My wife's definitely going to say I'm unfit for independent living.
And she'd be right. When you're in motion, you should think only about the motion. Movement is a dangerous force.
I'm not one of your silicon wafers. I'm human, and I'm hungry.
Perfect. Then you'll get it. Because yesterday, I solved a problem nobody could crack for 2 years. And guess what? It was all about movement.
You even turned a lunch into a seminar.
Just wait. This one's actually fun. You know how our vertical furnace works, right? We load 150 silicon wafers into a quartz boat, stacked one above the other. Then the whole boat enters the furnace from the bottom. There are 3 heating zones, top, middle, and bottom, each with its own thermocouple. Sounds tight. First, we flush the chamber with nitrogen to prevent unwanted oxidation. Then we stabilize the temperature and finally introduce oxygen, which forms a thin oxide layer on the wafers.
Yeah, and the bottom wafers always come out thicker. Worse yet, the sigma, the variation in oxide thickness, is huge. We tried everything short of replacing the furnace. 2 years of rituals and diagnostics.
Well, I also worked hard. For a full 2 days, I opened PRIZ platform and ran a brilliant tool. Process Functional Model. Broke the process into steps, built functional models for each. Boom. Loading and unloading, highlighted in red. Everything else? Green. But the real culprit was loading.
Wait, you're saying the issue happens when the wafer boat enters the furnace?
Exactly. During movement. Now listen carefully. Cold wafers go into a hot furnace, and the bottom thermocouple sees only the cold wafers and thinks the temperature dropped. So it cranks up the heat. Boom! Overheating. The bottom wafers are scorched before the rest even settle in. That's your sigma.
Unbelievable. So how do we fix it?
Simple. During loading and unloading, disconnect the bottom thermocouple from the temperature control. Let it watch but not interfere, like a mother-in-law at dinner.
Sometimes it's best to disconnect. If only we knew when.
This story perfectly illustrates how movement creates invisible problems that can persist for years, even in the most carefully controlled manufacturing environments. The engineers weren't looking at the loading process because it seemed too simple, too obvious. They were focused on the complex chemistry and temperature profiles during the actual oxidation process. But the real issue was happening in those few seconds when cold wafers entered the hot furnace, creating a false temperature reading that triggered an overcompensation response. The PRIZ methodology helped identify this by systematically modeling each process step and highlighting where the functional relationships were breaking down. Sometimes the most elegant solutions come from recognizing when to step back and let the system self-regulate, rather than trying to control every variable. The key insight here is that in complex systems, the interactions between components during transitions often create the most challenging problems, and systematic analysis tools can reveal these hidden dynamics that years of traditional troubleshooting might miss.
That brings us to the end of today's discussion, where we explored how movement can be a hidden issue in manufacturing processes, highlighting the innovative use of PRIZ methodology to resolve a persistent quality problem with silicon wafers. We hope you found value in our conversation and encourage you to like, comment, and share. Stay tuned for more perspectives on From QA Challenges to Innovation with PRIZ.